This video lecture addresses satellite remote sensing. Understanding the capture means of remote sensing data helps the image analyst with higher order image interpretation and in applications of environmental management and land use planning. Lecture content is based on materials from Campbell and Wynne, 2011, with supplementation from other sources as noted throughout and at the end of the lecture. In general, we think of two possible means of collecting remote sensing data, either from within the troposphere, which is the Earth's lower atmosphere, rising to roughly 12 kilometers, for example, through airplanes or ships, or in the outer layers of the Earth's atmosphere. The International Space Station and some other artificial satellites are in orbit in the thermosphere, which is a layer of the Earth's atmosphere starting at about 80 kilometers to an altitude range of 500 to 1,000 kilometers, depending on solar activity. Most of the satellites orbiting the Earth occur in the mesosphere, which is the outer atmosphere of the Earth extending up to 10,000 kilometers above the Earth's surface. For example, Landsat orbits at just over 700 kilometers above the Earth's surface at the equator. In the outer atmosphere, we consider the use of satellite remote sensing, although there are some other possible remote sensing platforms, such as photography from a manned space mission, which gave us the iconic Earthrise image shown here. The image is credited to the National Aeronautics and Space Administration, NASA, and was captured using a modified Hasselblad 500 EL camera by astronaut William Anders on December 24, 1968. In many ways, this image is one of the earliest, most influential snapshots of planet Earth and has been credited with driving the curiosity of mankind and influencing the environmental movements of the 1970s and showcasing the relevance of remote sensing perspective of planet Earth. The next several slides showcase many of the Earth observation satellites that have been used to capture remotely sensed data of the Earth's surface. As Campbell and Wynne, 2011 note, Landsat, or Land Satellite, was the first satellite launched specifically for broad-scale observation of land areas on Earth. The history and motivation behind Landsat are important in understanding how the system came into existence and how it has been sustained through current data collection. In cooperation, NASA and the U.S. Geological Survey, USGS, developed the first civil Earth-observing remote sensing satellite program with the launch of the first Landsat satellite in 1972. The Landsat program, with its 8 satellites over the past 40-plus years, has continuously collected spectral information of the surface of the planet Earth. EOEDU, no date. The entire Landsat image archive is available online for free since June 2009. This graphic from the USGS 2013 offers a chronology of Landsat remote sensing satellites. You can see several interesting things here, including the expected lifespan of Landsat 7 and Landsat 8 continuing perhaps past 2020, and also the loss of Landsat 6, which launched in October of 1993 but failed to reach orbit. Landsat 4 and 5 have extended lifespans, which helped compensate for the loss of Landsat 6. The specific sensors on each Landsat satellite have changed throughout the launch history. Landsat 1 through 5 carried the multispectral scanner, MSS, with an image resolution of approximately 80 meters in 4 spectral bands ranging from the visible green to the near-infrared, IR, wavelengths. The Return Beam Vidicon RBV, a camera-like instrument with low spectral and radiometric detail but high resolution and geometric accuracy, on Landsat 1 through 3 was designed to complement the MSS. Landsat 4 and 5 carried the Improved Thematic Mapper (TM) sensors, which collected data in several additional bands in the shortwave infrared portion of the spectrum. improved spatial resolution of 30 meters for the visible near-infrared and short-wave infrared bands, and added a 120-meter thermal infrared band. Landsat 7 carries the Enhanced Thematic Mapper Plus, ETM Plus, which is an improved version of the TM sensor. Landsat 8 carries the Operational Land Imager, OLI, and the Thermal Infrared Sensor, TIRS. The sensors on board Landsat satellites are considered passive sensors since they receive radiation reflected from Earth, but do not actively project radiation and read backscatter, as in active remote sensing, such as radar. France, in partnership with Belgium and Sweden, set up the SPOT Earth Observing System in 1978. EOEDU notes that the SPOT satellites constellation offers acquisition and revisit capacity, allowing to acquire imagery from anywhere in the world every day. Each SPOT payload comprises two identical high-resolution optical imaging instruments, which can operate simultaneously or individually in either panchromatic P mode, a single band in the visible part of the spectrum, or multispectral mode, XS mode, the green, red, and infrared bands of the electromagnetic spectrum. As with Landsat, SPOT has several generations of satellites with improved sensors for continuous operations and offering vertical and oblique viewing capability. IRS, or India Remote Sensing, Earth Observation Satellites also offer continuous observation of the Earth's surface starting with IRS-1A in 1988. The IRS-1A successfully launched into a polar sun-synchronous orbit on March 17, 1988 from the Soviet Cosmodrome. IRS-1A carries two cameras with resolutions of 73 meters and 36.25 meters, and a swath width of about 140 kilometers during each pass over the country. The IRS-1A mission was completed during July 1996 after serving for 8 years and 4 months. As EOEDU notes, India has one of the largest constellations of remote sensing satellites in operation today, and a wide variety of instruments flown on board these satellites. Major application of remotely sensed data from IRS includes agriculture, water resources, urban planning, rural development, mineral prospecting, environmental, forestry, ocean resources, and disaster management. The Advanced Very High Resolution Radiometer is a sensor that captures remotely sensed data in the visible, near-infrared, mid-infrared, and thermal infrared portions of the electromagnetic spectrum. 3 versions of AVHRR have flown on 3 U.S. satellites from the National Oceanic and Atmospheric Administration, or NOAA. Twice a day, the AVRHH-3, the most recent instrument, provides images of the cloud cover over the entire world. As EOEDU notes, AVHRR is well suited for vegetation study at the global scale, for example, through studying seasonal change. As well, AVHRR collects global data on sea surface temperatures and ice cover content. OrbView 2, also called Sea-Star, carries NASA's Sea Wi-Fi sensor, or the Sea Viewing Wide Field of View sensor, which was developed to study total chlorophyll content and eutrophication of the oceans. Sea Wi-Fi also collects remotely sensed data used to calculate the Normalized Difference Vegetation Index, NDVI. It flies in a sun-synchronous polar orbit with a 99-minute period of revolution and 1-day revisit time. GOI-1 is a commercial satellite with high spatial resolution, with a ground resolution of 0.41 meters in the panchromatic black and white mode and 1.65 meters in the multispectral color mode. Because of its high spatial resolution, imagery from GeoEye-1 is used in a wide range of applications. The satellite flies in a sun-synchronous polar orbit with a revisit time of under 3 days. As shown here for Chicago, Illinois, the combination of panchromatic and multispectral data offer color images with a resolution of 0.5 meters. Ikonos is the very first high-resolution civilian sensor providing images comparable to aerial photos with a resolution of 1 meter. Although the first Ikonos satellite was lost at launch in 1999, the second, also launched in 1999, is ongoing. Like GeoEye-1, Ikonos flies in a sun-synchronous polar orbit with a revisit time of 1.5 to 3 days. As EOE-DU notes, the very high resolution allows to visualize buildings, roads, or even trees, and is therefore very useful for applications such as urban cartography, land use, agriculture, and natural disaster management. This concludes our video lecture on satellite remote sensing. This is hardly an exhaustive list of historic and current satellites used in remote sensing, but it offers some insight into the rich history and depth of satellite remote sensing technology. The following references were consulted in developing this video lecture.